So we want to look at what we call periodic trends. And a periodic trend is something that deals with a property of the atom and how that property changes as we go across the periodic table and down the periodic table. Now the first one we want to look at is atomic radius. That just means the size of the atom. And if you have your handout, you'll see that I gave you kind of a little diagram that shows something like this. It shows circles getting bigger going down. Now hopefully that makes sense to you, because you know at this point that as you go down the periodic table, the number of protons and the number of electrons gets bigger. And so you would expect the atom to get bigger. Now specifically, as you stay within a family, when you go from here to here to here, you are adding one principal energy level each time. So if this just has like that, this one has like that. And remember that Bohr model that we've used so many times? And that's not a very good drawing, but anyway. So as you go down the periodic table, you add a new principal energy level every time. So that makes sense that they would be getting bigger. Now, what doesn't make quite as much intuitive sense is that as you go across the periodic table, the atoms get smaller. Now, you're still getting more protons and more electrons as you move across the table. Like if you look at the atomic numbers, you'll see that the number gets bigger. You add one every time you move from the left to the right. So you might think to yourself, well then, the atom should be getting bigger. But what's happening here is that we're adding electrons to the same principal energy level. Now, protons and electrons attract each other. So if we add more protons and more electrons in the same energy level, then we've got more attraction, and it's going to keep pulling in tighter and tighter. Now that effect is not going to be as big as the trend going down the table. Like the atoms are going to get significantly bigger as you go from top to bottom. As you go across, they're going to get smaller, but not huge amounts smaller. Partly because those electrons that are all together in that principal energy level, they repel each other. And so they kind of resist being pulled in tightly, but they can't resist totally because they really want to be close to the nucleus. So as we go across, we're going to see something like this where it's going to get smaller and smaller and smaller, but not hugely smaller, just a little bit smaller. So that's the trend for atomic radius. Now let's talk about the trend for ionization energy. Now, I did not define atomic radius because I'm pretty sure you know what a radius is. But ionization energy we need to define. It's the amount of energy needed to remove an electron. The amount of energy needed to remove an electron. And this tells us something about how reactive the element is going to be. Now I want you to think back with me to when we learned how to make ions. Remember we said that we can look at the periodic table, and just from its position on the table we can take certain elements and know whether they should be a +1 charge, a +2 charge, a -1 charge, and all that. And we knew that because we knew that all the elements really want to look like noble gases. So they really want to get that same electron arrangement as a noble gas. So we knew that, for example, in group 1A, all those elements just have one electron in that outer principal energy level, and they will lose that one electron. And as a matter of fact, they will lose that one electron very easily. So they have a low ionization energy. So if you just pretend I have the periodic table over here, we've got low ionization energies on the left because they very easily give up that one electron. It does take energy to get it off, but not tons of energy. Now, as we go across, it takes more and more energy to get these electrons off. So in general, we have a trend towards high ionization energies. Now, let's talk about why that's happening. Remember we said that as we go across the periodic table, the electrons get pulled in tighter and tighter and tighter to the nucleus. So doesn't it make sense that it would take more energy to get an electron away if it's tighter into the nucleus, if it's closer? And it takes less energy to get an electron away if it's very far away from the nucleus, because the nucleus is the thing that's holding it. So the further away you get from the nucleus, the easier it is to get that electron off. And that's why, as we go down the periodic table, it's going to get easier and easier to get that electron off. So as we go across, it gets higher. As we go down, it gets lower, it being the amount of energy needed to remove an electron. Now I know this looks a little funny because I put low and high both kind of in the same region, but these are all relative to each other, right? So as we go down the table, it takes less energy to get it off. As we go across the table, it takes more energy to get it off. So you can kind of see how this is working, where you can almost draw a diagonal line and say the lowest is here and the highest is here for ionization energies. So that's a big general trend. Now on the handout that you have kind of this jagged little graph that I gave you that kind of goes like this. That's a very bad picture, but anyway. And if you were in class, or if you will be in class, we worked through this idea together, and you were supposed to identify, or you will be identifying, what elements are here and here and here and here and so forth. Now the way you're going to do that is by thinking about how the elements are arranged so that we keep having to go back to a new row. Like if you're looking at the periodic table, just hold this up hopefully so that you can see it here. If you're looking at the periodic table, we get to the end of a row and then we have to start again. And then we go over here and we get to the end of a row and then we have to start again. So what's happening here is that it gets higher and higher and higher. In other words, it gets harder and harder and harder to remove that electron, and then all of a sudden we're starting a new row. Boom. So now we've got an element that it's easy to remove that electron because it's farther away from the nucleus. We're adding a new principal energy level. So this is way far away from the nucleus. It's easy to take that off, but then we're going to march across the periodic table. It's going to get harder and harder and harder until we get all the way over to the noble gases, and it's really hard to get a noble gas electron away from the atom, because now we've got a filled energy level and it's all really stable and everything. So we build our way up to a noble gas and then boom, fall back down again, and we start over with the alkali metals. So use that thinking as you try to take the graph that you have and figure out what are the elements here and here and here and here. You don't have to do all the ones in the middle, but I want you to look at just the ones in the peaks and the valleys. Now the last one is electronegativity, and I'm not really going to make any big effort to explain why these trends are the way they are, because that's kind of a subject for a higher level chemistry class. But I would like you to understand that electronegativity, you are very familiar with from a previous unit. Electronegativity gets higher going this way, and it gets lower going this way. So we could actually say that overall we have a trend going in this direction, where the lowest electronegativities are here and the highest electronegativities are over here. And that has to do with what we call metallic properties. Remember, metals are not that excited about keeping their electrons, and non-metals are, because they're very close to having a filled energy level. So they want to get more electrons to fill that up. So what's happening here is that we've got sharing going on. Remember, electronegativity was all about sharing for the most part. We're talking about within a bond, which one of these elements is going to pull harder. So an element with a higher electronegativity is going to pull harder. And this all related to how polar the bond would be. So that's a little review. We can think about that again. And it relates to then how polar the whole molecule is going to be. And that will tell us whether the molecules are attracted to each other, and that will tell us all about the properties. So this is material that we've already covered in a previous unit, and we need to go back and talk about that again. And that, I think, covers it for the different trends, at least the ones that we're going to learn about this year.